Okay, so today we're going to start talking about solving systems algebraically. So up to this point, we've looked at solving systems using graphing or using the calculator to graph and find the intersection point. Now, the value we're finding is still an XY value, and it's still where the two lines would meet if I were to graph them. There's still going to be a unique X and Y value. That's true. That is a solution to both equations. But we're not quite thinking about it in the same way. And so there's two ways that we're going to learn on how to solve these systems algebraically. The first being substitution method. So substitution, just like when we were substituting in for a variable, is exactly what it sounds like, where we're replacing something or substituting a value in for something else. So the only time that I use substitution method, and quite honestly, it's not the way I choose to solve a system most of the time. I use the second system that we'll learn. But I use substitution method when the variable, either X or Y, has a coefficient of 1 or -1. Okay, I don't really use it if they all have numbers. If it's like 2x plus 3y equals 7, then I wouldn't use substitution method, because using that method would create a whole bunch of fractions that I'd have to deal with. So really, this is only a method I would choose if, like here, I have just -1 or 1 for my coefficient for several of these variables. Okay. So in order to do this, what we're going to do, we're going to kind of fill in our steps as we go here. So the first thing we need to do is we need to isolate one variable in either equation. So it's a system, and I have two equations. So looking at the system that I have down below gives me equation 1 and equation 2. Now there's kind of several variables that would be easy to isolate here. I'm going to choose to isolate y in this equation by adding x over. Okay, so there's my step 1. Isolate variable. There's step 1. Okay, now that I've isolated that variable, now I can use substitution. Substitute the expression from step 1 into the other equation. So I've isolated a variable, and I now know that y equals x plus 1. So what I can do is, where I have y in my other equation, instead of writing 2x plus y, I can write 2x plus, and in place of y, I'll write x plus 1 equals -2. It's the same as if I knew y equaled 3, and I could plug 3 in for y. Now, it is a good idea to put it in parentheses in case there was a coefficient out front. Because it's just one y, I don't really need the parentheses there. So let me restate it one more time. Because y equals x plus 1, in my other equation where y is, I'm substituting in what it's equal to. Okay. And now I'm going to solve for x or y, depending on what you have substituted in. In the substituted equation. So in this equation, now I can solve for x, because I've gotten rid of having two variables here, and now I just have one. By substituting in, it allows me to solve. So like I said, I don't need this parenthesis, because it's just 1 there. So I just have 2x plus 1 equals -2, or 3x plus 1 equals -2. 3x equals -3, and x equals -1. Okay, so here's step, let me label this. Here's step 2, and here's step 3. Now, remember, our solution to a system is an ordered pair. It's where the two lines intersect. So I haven't finished solving. I've solved for x. So now I need to determine the value for the other variable and write our solution as an ordered pair. Okay, so now that I know that x equals -1, well, guess what? I can take that and plug it in over here and say, well, x is -1, so I can substitute that in. So we're substituting again. We took this and we substitute here. Then we solve. Then we took this and we substitute it back in. Okay, substitute in, allowed us to solve for x. Now we know that x is -1. We can substitute that in, and it gives me y equals 0. So I have an x and a y value, and I know that those lines must intersect at the point -1, 0. And just like when we were solving by graphing, I could plug that in and check. So I could say -1 is going to give me +1 plus 0. That works. 2 times -1 gives me -2 plus 0. That works. Okay, so I can still kind of do a check and see if this ordered pair works, and it needs to work in both equations. So let's look at another one. So first thing we need to worry about in our steps is isolating a variable. So in this example, there's kind of 3 possible variables I could use. So I could use x or y here because they both have 1 or -1, or I could use y in this equation. I think I'll isolate y in equation 1. So in equation 1, I could rewrite it as y equals x minus 4. Okay, so now that I know that y equals this, I can substitute it in for y in my other equation. So now this will look like 4x plus, and instead of y, I will plug in x minus 4 equals 26. And just like the one above, I'm just distributing 1 through, or I have a coefficient of 1 here. So I have 4x plus x minus 4 equals 26. Do get in the habit of substituting that in though. Like on this next one, it would be super important to have parentheses because I have coefficients going on there. That's going to give me 5x subtract 4 equals 26. For 5x equals 30. And x equals 6. So great, I have half of my solution. I still need to find y. So now I'm going to go back, x equals 6. I'm going to substitute that in here. I know y equals x minus 4, and I'm taking x and substituting in 6. So then y must equal 2. 6, 2. Okay. And I could check it real quick. So -6, right? Because plugging in 6 times -1, -6 plus 2 is going to give me -4 plus 4 gives me 0. Good. 24 plus 2 gives me 26. Okay, so I'm just doing a quick check up above before moving on. So now I want you to try to isolate a variable on B and substitute in and get your x and y value, and then I'll continue the video and see how you do. For this one, I would say there's only one variable I would isolate, and that would be this x right here, because it's just one x. The rest of them have coefficients I wouldn't want to deal with. Okay. Okay, so what I have here is kind of the beginning of solving this one, where I rewrote for x, and then I substituted that in. And then what we want to make sure we do is distribute through. So when I substitute x into my other equation, 3x minus 2y equals 4, I need to make sure that I substitute in and have those parentheses so that that 3 will distribute through. Give me -9y plus 15 minus 2y equals 4. And now I can solve for y here. So -11y plus 15 equals 4. or negative 11y equals negative 11 and y equals 1. To find x, I need to go and take this y equals 1 and plug it into my x equals equation up here, which would give me x equals negative 3 times 1 plus 5, or x equals negative 3 plus 5, and x equals 2. And then putting that together, okay, so these lines must intersect at 2, 1. Okay, so just to kind of see how that works, when I do have a coefficient where I substitute in, I need to distribute through. Let's flip this page, and it definitely looks a little more challenging, but it actually won't be too bad here. So what we're going to talk about is, well, what if I have a system like this first one where I have all sorts of fractions going on? Or what if I have all sorts of decimals going on? And so if you remember back to the first unit, we talked about the ability to clear fractions in an equation. So I'm just going to clear the fractions in both of these equations first, and then I'll have a kind of revised version of that system, and I'll go from there. So in my first equation, remember when we cleared fractions, it was important that we multiply the whole equation by that value. So I'm going to multiply the entire equation by 4 to get rid of my fraction. Remember, we use our LCD. So in this case, I only have one denominator, and I would multiply through by 4 to get rid of that fraction. Everything gets multiplied by 4, which is going to make this 12x plus a fourth of 4. It's going to give me 1y, and 2 times 4 gives me 8. So I cleared my fractions here. And for my other equation, I would also multiply, so the LCD here would be 4. I want to multiply the entire equation by that. 4 times 1/2, or 4 divided by 2, gives me 2x, plus 4 divided by 4 gives me 1, times 3 gives me 3y. 4 divided by 2 is 2, times negative 5 is negative 10. So now I'm no longer looking at this system at all. This is the same system, I've just rewritten the way it looks. So I've cleared the fractions. The values of x and y that are going to work out here will be the same. I've just gotten rid of the fractions and revised these equations. Okay, so from this system, I would isolate y because it doesn't have a coefficient in front of it, or it has a coefficient of 1. So I know y is negative 12x plus 8. And then I'm going to take that and substitute it in for y in my other equation. So now I'm going to have 2x plus 3y equals negative 10. And in place of y, and that's kind of typically how I write my substitution. I write out the equation. I write exactly what I have here, and I just need a space where I'm substituting in. And then I fill that space with whatever expression I have up above. So now I'm going to have 2x, and remember I need to distribute here, subtract 36x plus 24 equals negative 10. Combining like terms gives me negative 34x plus 24 equals negative 10. Subtracting 24 gives me negative 34x equals negative 34, or x equals 1. Now that I know x equals 1, I can take that and plug it in for x here. And I know that y equals negative 12 times 1 plus 8, or y equals negative 12 plus 8, y equals negative 4. Okay, rewrite it as an ordered pair. So these lines must intersect at 1, negative 4, which, like, having to graph those may have been a little hard if we had gone with the system we had used before vacation. Even looking at my cleared fraction equations, this one would be okay to graph, right? It'd be this line, that'd be fine. Here, I'd get a y-intercept of negative 10/3. So that wouldn't be super accurate in terms of my graphing, which is why we like to be able to solve algebraically, where we don't need to worry about the grids on the graph and knowing exactly where those lines cross, because the algebra will kind of find it for us. So now what I'd like for you to do, so on 2, we have one equation that's all set to go, that one's fine. On 3, they both have fractions. So first, I want you to pause the video, and I want you to just clear the fractions, and then replay the video and make sure our equations match. And then I'll give you some time to practice the substitution and solving. Okay, so right now you're just working on rewriting these systems, and then we'll see if our revised equations match. Okay, so here are my new systems that I'm going to work with. On 2, I had to multiply by 15 to get my revised equation. And on 3, I multiplied both equations by 6. And here my revised system. So now I'd like for you to pause again and go ahead and solve for x and y in these systems. And I'll show you my answers in a minute. Okay, so I have one of my systems totally solved, and I kind of stopped midway on 3. So here I solve for y. I plug that in. Now remember, we need to distribute. And I got x equals 2. And I wouldn't have solved for any of these other variables, by the way. This is the one that has the coefficient of -1. So I should have solved for this y. And when I substitute in 2 for x, I get -3 for y. Now in 3, I have some options. I would think you could solve for either x or y here, so that's up to you. I chose y, so I rewrote it for y, and then I plugged that into this equation. And then here, when I distribute, I need to be careful because I have a negative out front. So it's going to become negative times a negative is going to give me positive 2x. Negative times a positive is going to give me -24. So just being really careful with that sort of thing still as we do this work. Combining like terms, that gives me -1x minus 24 equals -48. Or negative x equals -24. And x equals 24. Substituting that in for my other equation. So -24 plus 12 would give me y equals -12. 24, -12. Okay. So now we're going to look at similar idea here, but what if we had decimals? And so remember, when we clear decimals, we multiply by 10, 100, 1,000, okay, whatever we need to get rid of the decimals. And actually, let's add that to our notes just so we have it on the other page. To clear fractions first, we multiply by the LCD. Okay, that's how we clear fractions. This is how we clear decimals. And so for this first system, I'm just going to rewrite it like we did with the fraction ones. I only need to move my decimal place over 1. So I'm going to multiply by 10, which would give me 5x plus 24y equals 42. Same here, I only need to multiply by 10, which would give me -1x plus 15y equals 51. Now on this system, this would be the variable that it would make sense to isolate. So rewriting that would give me x equals positive 15y minus 51. And I kind of did 2 steps there. So I subtract 15 over, and then everything gets divided by -1. So if x equals that, then in my other equation, 5x plus 24y equals 42, I can take that and substitute it in place of x. Okay, so now distributing through, so let's see, that's going to give me 75y, subtract 255 plus 24y equals 42. Combining like terms, this is going to give me 99y minus 255 equals 42. And adding 255, 99y equals 297. Divide by 99, and that's going to go in 3 times, I believe. Yeah, 3. So now that I know that y is 3, I can go back and substitute that in to my x equals equation. So instead of 15y subtract 51, now I have 15 times 3, or 45 subtract 51, which is going to give me a -6. And I have -6, 3 for my ordered pair there. Okay. So now, I mean, we've done a lot of solving today, so I'd like for you to go ahead. We'll pause, rewrite your systems first. We'll check them, and then I'll let you fully solve them, and we'll just check answers and move on. Okay, so just real quick, check your systems on 5 and 6. On 5, I multiplied both equations by 10. Make sure you multiply all of the terms by 10, so like don't leave out that -2, becomes -20. And on 6, I had to multiply by 100 to clear my fractions, and there's my revised system. Okay, so again, I want you to pause the video and then go ahead and solve these two systems. Okay, so let's look at our two systems here. So on 5, I get 7, -3, and if you need to pause it and kind of look at my work here, you can do so. And on 6, I have 20, 30. And get some larger numbers here, but it does work out nicely in the end, 142. Okay, I can see that that's just 2, that's doubled, and add a 0, 20. Okay, doable, larger numbers. So there's one more thing I want to discuss quickly before ending the video, and that's that systems aren't always going to intersect. Okay, so something that happens is that we do have some special types of systems. And so you'll see the first case there, that's exactly what we've always seen up until now, where my two lines, and I don't know why they're dashed lines, there should be solid lines. My two lines intersect. And in that case, there's going to be one solution. It's an ordered pair. Every single system we've looked at so far has been this case. But what if my lines are parallel? And so we have parallel lines have the same slope, then the system has no solution. These lines are never going to meet. They're never going to have a common XY value. Okay, so if the lines are parallel, there's no possible solution to that system. Okay. Now the last case is kind of hard to see on the graph. What's happening on the last case is I have a line, and then if I were to graph the same line again, I'm looking for a different color, it would end up being the exact same y-intercept, same slope. The lines coincide, which means the two lines lie on top of each other on the same graph. In this case, every single point on here is an XY value that will work for both lines. So if the lines, what we call coincide, that means there's infinitely many solutions. Every point on one line is a solution on the other line. So what we're going to start seeing is solving by graphing or solving by substitution, where these cases show up. So the graphing piece, it's going to be much clearer. So let's look at our two examples here. Rewriting y equals -2x plus 5. So go 1, 2, 3, 4, 5. Slope of -2. My other equation would be y equals -2x plus 1. And I go, oh, hey, they have the same slope. So these lines will never intersect, right? Those are called parallel lines. So if I graph and I get lines that aren't going to meet, and I verify that they have the same slope, right? So sometimes our lines just meet like right off the graph, and we want to make sure that that's not the case. But we have the same slope, means they're parallel. We see they're parallel. This is no solution. What lines coincide would look like, here rewriting y equals 2x plus 3. You may not be immediately aware that its lines coincide. Here it was, we could kind of see it at the beginning. But here, these don't look like the same line right now, right? But when I go to rewrite my other equation, so 2y equals 4x plus 6, and then divide by 2, look at that. It's the same line. So when I go to graph that line, y-intercept at 3, slope of 2, it's right on top of the other line. Okay, that's what lines coincide mean. So this would be an example of infinitely many solutions. So graphically, it's really easy to see when I have a special case. Algebraically, it's not quite as simple. So here we're going to solve using substitution method. I already have a y equals here. So I'm going to take my other equation, and where y is, okay, 4x minus y, I'm going to substitute in what y is equal to. Now this one's a little actually tricky setup when it's just negative y here, because I need to make sure that I distribute that negative 1 through when I'm solving by substitution. And then this gives me 4x and negative 4x is just going to cancel out. And it gives me negative 3 equals negative 3. And that's a true statement, right? This is an infinitely many solution. So just like when we had the special cases when we were solving for a single variable back in unit 1, same kind of idea where like if I solve and all of my variable terms cancel, all variable terms cancel. Okay, in order for it to be a special case, if I'm solving algebraically, all of the variables cancel. So I have no variable left. I just have this statement, which happens to be a true statement, which means I could literally plug anything in here and it's going to work out okay. And I could double check it. I can like, in my mind, I would look to make sure they're parallel. Or I'm sorry, that their lines coincide, not parallel. That when I rewrite this, that I would get the exact same line, which I would. I'd have 4x plus 3. So they're the same line. There's every solution for one line would be one for the other. On my other case, so again, I already have solved for one of my variables. So in where x is, I'm going to substitute in what x is equal to, which is 1 minus 5y. I'm just plugging in, distributing that 2. So I get 2 minus 10y plus 10y equals 3. Negative 10y, positive 10y. Again, that happened, right? All of the variable term canceled. And I'm left with 2 equals 3, which is not true. False. Okay. So algebraically, when we solve, we're not going to see the visual of parallel or lines coincide. What we're going to see is my variable terms cancel, and either I have a true statement, infinitely many, or all my variables cancel and I have a false statement, which would mean there's no solution. There's no way, there's no XY value that's going to work for that system. Okay. So when you do some practice now, you may run into one of these special cases and you want to get familiar with which one looks which way.